Hi guys, welcome back. This is going to be the start of our videos on the Earth systems and the dynamic Earth. We're going to be covering the structure of the Earth in the start of this video here. And then this series is going to progress on to talk about our atmosphere, hydrosphere, and biosphere. But first we need to start out with the geosphere, and that is the physical and rocky part of the Earth, all the way down to the center of it. All right, so let's get going. All right, so the essential question for this part and the goal that we're going to try and cover is how is the Earth constructed? What are the layers of the Earth and how do they relate to one another? How are they different structurally, chemically, and physically? So we need to start out with an understanding of basically just how is the Earth structured? What is it made of? And what are the properties of its different layers? So let's take a look at what the Earth is made of. And we have three main layers to the Earth, and I want to break those down for you. You start off on the outermost layer of the Earth, where you guys are walking, sitting, or living, whatever, right now. Okay, this is where you have the surface, which is where it meets the atmosphere, where we have the water existing, and all life on Earth, for the most part, is on the surface, and even life that you find underground in that solid rock that's surrounding the outermost part. That's still the crust of the Earth. The second layer is going to be the mantle, and this is going to be a layer on the inside of the Earth between the crust and the last layer, which is the core. All right, so let's break down what these look like. The crust is the outermost layer. It's between 5 and 100 kilometers thick. It is actually the thinnest of the layers, and it accounts for only about 1% of the Earth. This crust is like the cooled outside of a piece of, hot, semi-molten something, all right? It's like the balloon in a water balloon, all right? It is only the outermost layer, and the majority of the mass of the Earth is actually located inside of it. Second, you're going to have the mantle. The mantle accounts for 67 to 70% of Earth's mass. It ranges a little bit in thickness, actually, so it can vary in thickness still, usually around 2,900 kilometers thick, but there are parts of it which are thicker and thinner, depending on the shape of the crust, and, it's an average, but when you get up to something that big, a difference of 5 to 10 kilometers does not make as much of a difference. And then lastly, you have the core of the Earth. We've got actually a pretty good precise measurement of this. It is roughly spherical in shape, roughly, I say. It's about 33% or 1/3 of the mass of the Earth. It is a more liquid in its outermost part than the mantle, which is generally softer. But those are the general layers of the Earth. And what we're going to do now is we're going to dive into each of these layers, if you'll pardon the pun. And we're going to try and look into these and see what the properties are of each one. So let's take a look at that and check that out. All right, so the first layer we're going to start with is, because we're going to be working from the outside in, is the outermost layer, which is the crust. The crust is the outermost layer of the Earth. As I said, it's the thinnest part. It is where you'll find the hydrosphere, so you get the oceans there, and then you get the land, and it is shaped by tectonic forces, and this outermost part is where you, me, and everything we know is going to live. Under the oceans, it's called oceanic crust, and under the land, it's called continental crust. These do both move around and they interact with each other, and we'll talk about that when we talk about earthquakes and volcanoes. All right, so looking at the crust, you've got to realize that it is actually the thinnest layer of the Earth, and there's parts of it that are only about 2 miles thick. That is where you can find the thickness of the crust at some of the deepest parts of the Earth's ocean. Under those very, very deep parts of the ocean, the crust actually dives down. It is much thinner, and that's why the ocean's deeper there as well. It is made up of mostly silicon and aluminum. Those are actually the two most plentiful elements in the crust of the Earth. Silica is basically what sand is. It's also what's melted down to make glass. And then you have two types in there, as I said before. We break that up into talking about oceanic crust and continental crust. There are some slight differences in them in terms of composition, what they're made of. That actually does make a little bit of difference in terms of how they settle out and why you generally have uplift on one and subduction or diving of the other part of the crust when they meet. It is broken up into what are called continental plates, or just plates, on which the continents and the oceans rest. These plates are moving. They are being moved around, and as they move, we get a dynamic shaping and changing of our land masses throughout geologic time. So what's moving them? Well, it's what's going on in the mantle. Now, the mantle is divided up into three sections. So there are three main sections to the Earth itself, but the mantle, which is the middle section, is also divided up. Just like under the crust, you had the oceanic crust and you had the continental crust. In the mantle, though, it's divided by depth. So the lowest layer is the lower mantle. The middle layer is the middle mantle. I know, such a creative name, right? And then the topmost layer is the upper mantle. But where we want to look is actually going to be in that middle layer, and that's where we have convection currents. Now, the term convection is going to come around a couple of times. We're going to talk about that a bunch, but convection is just the circulating of heat, all right? Convection is the circulation of heat in a fluid specifically. That is how fluids will change and move as you heat them up. Maybe you've looked at a pot of boiling water or something like that, and you've noticed that it's got this bubbling where it seems like stuff's coming up from the bottom and moving around like that. Well, that's a type of convection, all right? In air, hot air will generally rise. That's why a hot air balloon works. And cold air will generally sink. Well, guess what? In the semi-liquid phase in the middle of the mantle, all right, that is going to have the same thing. You're going to have the hotter parts down at the bottom, closer to the core, where it warms up. It starts to rise up through the mantle. It cools, and then it settles back down. Okay, so I want to take a second here and actually see if I can explain what the consistency of the mantle is like. So I've got this stuff here. It's slime. This is actually one of my son's toys. He got it from some prize thing, won it at like a fair at his school or something. And it's kind of gross and it smells weird, but you know what? It's actually pretty perfect for this. So this stuff, if you look at it, you see that it flows and it's goopy like this. I don't know if you guys ever had a toy like this when you were a kid, but if you look at it, it's this weird gelatinous stuff, right? And it's a little sticky, but here's the thing, it's not a liquid. See, it'll cling like that and then flow, and it can stretch and deform and be all jiggly and stuff. And you know, it's kind of strange, but this is basically what the mantle is like. This kind of like jiggly, bouncy stuff, like some sort of weird jello almost, all right? Now, obviously, the mantle is several thousand degrees, and it probably wouldn't be as elastic and jiggly and bouncy, because this is like made of like rubber-like substances, but you get the idea that it is this squishy material that that is not totally liquid, not totally solid. It can flow, it can deform, it takes the shape of whatever it's in, but it's also not completely liquid, all right? It still has some kind of semi-solid properties to it, and that's going to be important when we talk about what the effects of this convection are, because it is thicker all right? And it can put a lot of mass behind it when it starts pushing and flowing because it is semi-solid rock. All right, so let's talk about the mantle. So I mentioned previously that we have these convection currents, and that's that circulation of heat. And maybe you guys have seen one of these before. This is a lava lamp. You've probably heard of them. But a lava lamp is named that because the liquid inside here kind of looks like lava. But interestingly enough, it actually behaves very similarly to how the convection currents inside the Earth behave. Now, the way a lava lamp works is you have a jar or liquid container that is filled with usually water. It might be dyed different colors, but generally it's clear. And then you have this stuff in here, and that's actually a type of wax. And then down at the bottom of the jar, you've got a metal coil, and this sits on top of an incandescent bulb, an old-fashioned bulb that gets really, really hot, okay? So the way that this lava lamp works is this bulb heats up. As it does, it melts the wax, and the wax, as it melts, becomes less dense. Because it's less dense, it can now float up to the surface, where it will then cool and start to descend back down. So this action that you'll have in here, where you'll have globs of the hottest part of the wax separating, coming up to the surface, cooling, and then coming back down, that happens inside the mantle as well with the convection currents. In fact, this is almost exactly like what's called a hot spot, where you will sometimes have volcanoes forming in the middle of continents as a result of this kind of heating of the magma rising up, going up to the surface, and then violently sometimes exploding. The best example of a hotspot volcano on Earth is Hawaii. The volcanoes on Hawaii behave because of this kind of convection. So let's show you guys what this actually means for the Earth. Let's break this away from just the diagram here and the model of a lava lamp, and let's take a look at the actual mantle. All right, so it is solid but capable of flow, like asphalt or fudge or something like that. So it's kind of soft and goopy, but it's able to move. All right. It is the thickest layer of the Earth. It makes up about 70% of the Earth's mass. Like I said, it makes up between 67 and 70%. Kind of depends on the thickness there, and the estimates vary depending on how you judge where one boundary layer starts and another one stops. And it is made of hot material, magma. All right, so while this is called a lava lamp, what you need to understand is that when that rock is molten and underground, it is called magma. When it comes out on the surface, it's called lava. Those are two very different terms, and we will discuss that in a little bit, probably next video or two. We'll talk about volcanoes and earthquakes, but I want to make sure that you know the correct terms for those. All right. In the mantle, the magma rises up to the top, cools, and then sinks, reheats, and rises again. And these convection currents are actually what help change the Earth's surface. So as they're moving up, they're going to push against the crust, and they're actually going to help move the crust around. So after the mantle, the next part you're going to have is going to be the core. And the core is divided up into two layers. So if you remember, all right, we have the crust, which is broken up into oceanic and continental. We have the mantle, which is divided into the upper, middle, and lower mantle. All right. And then we have the core. And the core is divided into the outer core and then the inner core. All right, so you have the outer core and the inner core. The inner core is the centermost part. The outer core surrounds it. Now, even though these are both the core, they actually have very, very different properties. All right, so let's take a look at them and see how these differ. So starting with the outer core, we can see that you have a molten or liquid metal that is around 4,700 degrees Celsius, which is about 8,500 degrees Fahrenheit. And this is a mixture of a lot of metals. Again, it's probably going to be mostly iron and nickel. And here you're going to have probably some aluminum and a couple other materials as well. It's located about 1,800 miles beneath the crust, and it's about 1,400 miles thick. It is composed of the melted metals, again, nickel and iron, mostly, although you will get traces of other metals in there as well. The deeper you go inside our Earth, the more likely you are to encounter nickel and iron, although you will also get a mixture of other heavy metals. These metals are extremely abundant, so nickel and iron are both very, very abundant metals throughout the universe and throughout space. It is thought that as our planet was forming, the larger amounts of those congregated together through magnetic interaction, because remember, iron is magnetic, so it'll clump together through that, but also then through gravity as it developed a larger and larger gravitational force. So you're going to have those out there. I want to note that it is liquid. It is fully liquid. So this is about the consistency of pancake syrup, but it is a liquid. It will flow, all right? However, the inner core, the centermost part, is actually a solid sphere composed mostly of iron. It's believed to be as hot as 12,000 degrees Fahrenheit or 6,650 degrees Celsius. And its heat is probably generated by radioactive decay. The idea here is quite simply that some of the heaviest elements were still able to sink to the center of the core, where they congregated in a large enough amount that you actually have nuclear fission reactions undergoing in the core, which is supplying our core with heat continuously. This is thought to be the reason why our Earth has not cooled off in its center. Not just because it's big, not just because it's got a lot of material around it. The reason why our core is still hot like this is because it is being supplied with continuous energy from these radioactive elements. Now, the last thing, though, that we need to note on here is that the pressure from all of the metal around it, because think about it, you are now several thousand kilometers underground, all right? You've got a huge amount of energy and force and material just from gravity crushing down on it. And so it's solid. The outer core was liquid. The mantle around it was like putty or asphalt, all right? It was all goopy, all right? Right? Remember, it was all goopy. But the center, the core, is solid, like a solid iron ball that's got these other impurities in it that is just blazingly hot, all right? So even though the outer parts are increasingly liquid, once you get to the center, that density goes way back up, and because it's so under so much pressure, it can't become a liquid. It gets compressed back into a solid. All right, so let's review. The Earth is made up of three main layers. All right, and let's see if we can review what those layers are. So working from the outside in, first you have the crust, which is going to be the thinnest layer. The mantle is in the middle, and it's going to be the largest layer, and it's semi-solid. Remember, it's squishy, gooey kind of thing. And then you have the core, and you're going to have a liquid outer core and a solid inner core. All right? So we want to review and remember that the crust is on the outside, mantle is in the middle, core is in the center, and you want to make sure that you know what the properties are of those. That generally speaking, you're going to have a solid crust, squishy mantle, liquid outer core, solid inner core. All right, guys, that's where I'm going to end this video. We'll be back in 2 days with a video on the nature of convection and how it affects our tectonic plates. And then we'll continue on to talk about earthquakes and volcanoes. All right. Take care. You have a good day, guys.